So one-dimensional force problems, stuff in a straight line. And by straight line, Julie, I mean up and down or left and right, because you could argue slanty is a straight line. We're not going to get there yet, eventually. Some important one-dimensional force problems include the elevator problem. What the elevator problem asks is, how heavy do you actually feel? It's your apparent weight, except we had a fancy name for apparent weight. We'll talk about that in a second. Air resistance, friction, and the many body problems. We'll, more than one mass. We'll devote a separate lesson to friction. We'll devote a separate lesson to more than one mass. But if we do our jobs right, it won't be a surprise. It'll be more of a, oh, that makes sense. The normal force. The normal force is the contact force between the floor and the object. In fact, it's the force that you feel right now between your feet and the floor and between your chair and your seat. It's what you feel pushing back up on you to counteract gravity's pull down. Or if you push sideways against a wall, the surface pushes back. It's the Newton's third law, forces come in pairs, reactive force, that an inanimate object applies when you're applying a force onto it. So it's the force with which the floor pushes on you. Interestingly enough, the normal force is also the value that a scale would read if you were standing on it. And I tried to drum this into your ear. I said that scales don't read weight, they read normal force. Pause the video for a second and I'll show you. Another term, another synonym for the normal force, we often call it the apparent weight. Your actual weight is mg. Your apparent weight is how heavy you feel, which varies. You'll pay good money for an amusement park ride because all an amusement park ride does is muck around with the normal force. I showed you a video last year of a kid on their first roller coaster ride experiencing his first change in the normal force. Remember that? If not, I'll show it to you a bit later. So normally, no pun intended, right now for all of you, your apparent weight and mg are identical. You know how I know? Newton's first. Are you sinking into the realm like quicksand? Are you flying in the air like Superman? And that's really why I asked that dumb phrase last year. I wanted you to recognize that in this situation right now, forces are balanced. If gravity's pulling you down, the ground must be pushing you up, and they're identical. When you jump, which way do you push? With your feet, which way do you push when you jump? Think about it. Which way do you accelerate? Which force accelerates you? So what happens is gravity's already pushing down on the ground. You push down, and so now there's a bigger force on the ground. Forces come in. The ground will push back up with that bigger force, which is bigger than gravity, and the extra force is enough to get you to accelerate off the ground. And if you think it's your legs that make you jump, try sitting on a step stool and pushing your legs down. I assure you right now, I'm not leaving the chair, even though I'm pushing down with my legs. It's the ground pushing back up, right? So all an amusement park ride does is muck around with a normal force. Put your pencils down. So now we can go to a question that a lot of kids struggled with last year, but hopefully now is a bit more obvious. The elevator question. If a person with a mass little m, I told you we're going to do more algebraic questions, and a weight w, remember weight is a synonym for mg, is in an elevator standing on a bathroom scale, and just to make it easy, let's pretend this scale measures in newtons, not in kilograms, so we don't have to do the conversion that Liam did. If the elevator starts at rest and accelerates up, what will the scale read? W more than W, less than W? What do you think? Convince me. He's right, but that's too many words. This is a job for a good free body diagram, I think. So here's the person. What are the forces acting on this person? Drake, get the obvious one. Absolutely. Now, normally I call that mg, but since they wanted me to call it w, I'll use w this time. Yes? But which way are they accelerating? So there has to be, from Newton's first law, there has to be a bigger arrow pointing up, yes? And this is the normal force, and you can even draw an arrow. Remember, that is what we call the apparent weight. It's also what the scale is going to read. If we wanted to write an equation, who's winning? Okay, so if we wanted to write an equation, and by the way, Connor, I would totally take your explanation, but too much English. I think now I can go like this. Fn minus W equals ma. And since it's talking about the scale reading, which is the normal force, Robbie, we want to get the normal force by itself. How do I get the normal force by itself in this equation, my friend? Okay, so here's my final argument. The normal force is equal to your weight plus ma. When the elevator is at a constant speed, what's the acceleration? And this would vanish. Don't cross that out, don't cross that out. But when the elevator is at a constant speed, it would vanish. This is why Einstein said there is no experiment that can prove whether you're at rest or moving at a constant speed. Because you could be at rest, you could be at a constant speed. However, what we can detect is acceleration. That we can detect. And since normally it'd be that, we're adding to it. Therefore, Fn is, oh, you know what? Why would I write is greater than W? I can even do that, bring out the full math. No English in that answer. And again, I would totally accept your. Example 2 says write a net force equation for the situation described in example 1. Done, right there. Fn equals W plus ma. Or Fn minus W equals ma. Already did it. That's the other reason I chose to go this route, is I glanced at example 2 and said, why don't I kill two birds with one stone? Okay. We can put numbers in if you wish. 35 kilogram student stands on a kilogram scale. If the elevator accelerates down, I would probably underline down just to remind myself. Find the normal force, find the scale reading. Okay. You know what this is a job for? Good free body diagram will represent the person with a dot. What are the forces acting on this person? Get the obvious one. mg down. By the way, I'll always say get the obvious one. I may have mentioned this last class, I can't remember. A few units from now, when we're in outer space, I will still say get the obvious one, and then we'll pause and we'll say, oh, wait a minute, we're in outer space. Sorry, no force of gravity way out there. So don't always assume it's there. Or if we're in outer space, we'll have to use the cosmic equation for gravity, which sadly is much more complicated than this one. Is this person in free fall? How do I know? If they were in free fall, what would it say the acceleration was? Does it say 9.8? So there has to be a force up. Is it going to be bigger or smaller or the same size as mg? The arrow that I draw, is it going to be bigger, smaller, or the same size as mg? How do you know smaller? Down. Not down, really. Right? Accelerating, yeah, but down. So I'll exaggerate it just so it's really obvious. And Sarah, in this question, it's going to be more convenient to let down be positive. Which force is bigger, Sarah? Gravity. That's going to be my winner. So my equation is going to be, for part A, winner minus loser equals ma. Kayla, what does this question want me to find? Part A? Remember that we did this last year a bunch. We plus that there at the same time, minus that there. Can I do that in one step? Yeah. So I think I'm going to get this. The normal force equals mg minus ma. I'll do a quick double check, Robbie. Do I know m? Yep. Do I know g? 9.8. Not negative. I took care of the negative with my winner minus loser. So this unit, this in forces, we're not going to put in a negative 9.8 because we're not always letting down be negative. In this case, we let down be positive. I know the mass. Oh, and A is 2.25. Plug and chug. It's going to be 35, 9.8 minus 35 times 2.25. I get 264.25 to 3 sig figs, 264 newtons. What does B want me to find? How can I change newtons to kilograms? Okay. I'll do B up here because I have room. I'm going to take 264. I'll use the 0.25 as well. Divide by 9.8. And this is what Liam experienced or noticed when he was doing the deep knee bends. The scale does move. The reason it moves is because the normal force changes, not because your mass changes. So the scale would say, you know what, 27.0 if I go to 3 sig figs, because the 9 gets rounded up. Even though this person has a mass of 35 kilograms, they would feel lighter. Mr. Duick, I don't notice this in elevators. That's because most elevators only accelerate for a split second, and then you're at a constant speed. But on good express elevators, you'll notice it for a little bit at least. Example 4. Connor M., what does example 4 want me to find? You know what this is a good job for? Although, did they give me a picture? Rather than do a completely separate free body diagram, I'm going to label the forces on this picture, which technically isn't a free body diagram, but I'll treat it as though it is. I think I can figure it out. So what are the forces acting on this box? Connor, get the obvious one. What else? Well, there's that 15. See it? Pointed which way? Okay. What else? Is this box sinking into the ground like quicksand? Is it flying into you like Superman? So things have to be balanced. Why would this be wrong? Why would it be wrong if I wrote the normal force the same size as mg? Ty, you with me? You're not on your phone or anything foolish right now, are you? Put it away. Oh, you weren't on your phone? Okay, I apologize. Why would that be wrong, what I just drew? Okay, the normal force is going to be bigger because someone's pushing down. So I always tend to try and exaggerate, so I would go, yeah, really big normal force. What's my equation? Who's winning? Are we accelerating at all, Connor? So technically it's a tie. So you could either go like this, everything up, winner, minus everything down equals 0, and that's perfectly acceptable. Or because it's a tie, if you want to, if you can see it in your head, Sinead, I'm perfectly fine if you just say, you know what, the normal force equals those two added together. Everything up equals everything down. In fact, that's probably what I would do. I would plus this over. In fact, I would do that. So it's going to be 15 plus 5 times 9.8. 5 times 9.8 is 49, 59, 64. Double check me. Yeah. Slightly bigger normal force than normal. And I realize I'm using the word normal twice in 2 different contexts there, but slightly bigger normal force than usual there. That's what I should say. Given the net force acting on each object, it says fill in the missing forces on the free body diagram and then circle yes or no if the object is accelerating. You know what? Let's do the yes or no part first. I can easily tell whether the object is accelerating or not. If we're not accelerating, what's my net force? Not accelerating, 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 because for the next 3, it says there is a net force, 900, 60, and 30. It must be accelerating. This is the tricycle question all over again. I'm not going to overcomplicate it. Unbalanced force, it's got to accelerate. So, in the first diagram, if you know the net force is 0, how big does force A have to be? Yes? How big does force B have to be? Has to be 200 newtons. Yes? Yeah? You're not using a calculator for this, are you? Please, I hope not. Connor, without a calculator, if the net force is 900 newtons up, how big does force C have to be in your head without a calculator? Oh, thank you for restoring my faith. How big does force D have to be? How big does force E have to be? How big does force F have to, you know what, let's do G first. How big does force G have to be? Algebraically, how big does force F have to be? And how big does force H have to be? Because, is it sinking around like quicksand? Is it flying here like cement? No, the Newton's first says it's got to be balanced. Air resistance is another force. Air resistance is the force of air molecules bumping into an object that's moving through the air. And the key idea, air resistance has direction opposite to motion. So we did this last year, but it's worth repeating. It says, draw force diagrams for each of the following. A ball being thrown, a ball on its way up, rising, and a ball on its way down. So for situation A, I mean this portion while I'm throwing it. For situation B, I mean on the way up, C, on the way down. Okay? What are the forces in situation A? Get the obvious one. Okay, so I would have gravity down. We could call it a normal force because it's a surface. We call it force throw. Well, you know what? Here's my question. Will the arrow that I draw pointing up be bigger, smaller, or the same size as mg? If it was the same size, this would happen. If I want the ball to leave my hand, well, while I'm holding it still, I'm telling you, if I go the same size while I'm holding it, at the end, this will happen. It's not going to go anywhere. So you want to revise your answer? Which way, does the arrow have to be bigger, smaller, or the same size? That's how you throw something. You apply a bigger force to the object than gravity pulling down. So you can call it throw, you can call it normal force, whatever. I'm not going to be fussy on that. We're not going to really look at that. I'm going to ignore air resistance during the throw. I'm going to say that the hand is kind of absorbing it all as well. But really, I want to talk about air resistance in part B and part C. We ignored it for projectiles all the time. What are the forces on part B on the way up? Get the obvious one. James is awake. Is Drake falling asleep? No? No, he's awake. I'm checking his eyes. Trust me, I'm armed and dangerous here. I'm ready to fire a Nerf dart gun at him. People on YouTube, what? Yeah. What else? Which way is the ball moving? Which way would air resistance be then? So I'll draw that a bit off to the side, and I know air resistance is smaller than gravity. Gravity is really what slows the object down. Air resistance plays a role. Anything else? Shouldn't there be a force pointing up? It's moving up. And this is a really tough one to get people to wrap their minds around. Even when I talk to science teachers that have taught physics, some of them will say, oh, there must be a force pointing up. I don't care about the direction of the velocity. I care about the direction of the acceleration. It's slowing down. It's accelerating down. The forces are pointing down. C, what are the forces acting on it? Get the obvious one. What else? Which way? Bigger, smaller, or the same size as mg? What if it was the same size? No. Constant speed. I've Jumped out of an airplane. I mentioned I jumped out of an airplane. We have a fancy name when air resistance is the same size as gravity. We call it terminal velocity. But I assure you, I wasn't hovering up there. I was not. What if it was bigger? Can it be bigger? Isn't parachute same size? Ah. What was that? Instead of slowing down, can you say accelerating and a direction? When I pulled my chute, imagine I jumped out of an airplane. When I pulled my parachute, when I slowed down, for a while, my air resistance was larger than gravity because I was accelerating up. Now I had an initial negative velocity, so I wasn't physically moving up. I was slowing down. And then the equilibrium point typically is when air resistance equals gravity. The idea with a parachute is terminal velocity is much smaller. In fact, hopefully with a parachute, terminal velocity isn't so terminal, so to speak, right? So example 5 says, in 4b, how can the ball be rising if all the forces acting on it are downwards? And I'm just going to say, don't confuse velocity with acceleration. The acceleration is what tells you the force direction, not the velocity. Now, if you keep accelerating long enough, eventually your acceleration and your velocity will end up in the same direction, eventually. But not always right away. Example 6 says, if the ball in 4c is speeding up, accelerating downwards, write a net force equation. Who's winning? Who's losing? And that would equal ma. And if I knew some of those numbers, I could calculate something. In fact, let's look at a parachutist. I've jumped out of an airplane. I jumped out of an airplane. A 90-kilogram parachutist free falls for a while and opens the parachute. If the parachutist slows down at a rate of 1.5 meters per second, if I'm slowing down, which way am I accelerating? I'll just make a little note there. A says, compare the forces that act on the system. You know what? That's really a fancy schmancy way, Drake, of saying, draw a free body diagram. Hey, what are the forces acting on this parachutist? Get the obvious one. What else? Air resistance bigger, smaller, or the same size as gravity? If I'm slowing down, if I'm accelerating up, it must be larger. Cool. Nick, what does B want me to do? Who's winning? Who's losing? What does that always equal? The net force, which is just ma. There. Hey, Riley, what does C want me to find? Oh, get the F air by itself. Riley, how would I do that? Yep. Air resistance is going to be mg plus ma, or ma plus mg. Now, terminal velocity is when a is 0. Don't write this down, just watch. There's terminal velocity. When that occurs, that will occur at terminal velocity, whatever the heck that is. Because air resistance, how big it is, does depend on how fast you're traveling. We're not going to ever calculate air resistance using the drag coefficients, velocity. There is an equation for it. We can find it indirectly like this. It's going to be 90 times 9.8 plus 90 times 1.5. Can I do that in my head? I can factor out a 90. It'll be 9.8, it'll be 10.8, it'll be 11.3. 11.3 times 90, 991,017? Or am I wrong? I could be totally off. I'm right? To 3 sig figs. Let me pause for 1 second. Next page. The force of air resistance is actually not a constant value. In fact, the force gets larger as speed increases. So a falling object will eventually reach the point where the force, if I mean to correct that, of air resistance equals the weight. And remember, weight is a synonym, Rob, for mg of the object. At this point, it will hold a steady speed that we call terminal velocity. Air resistance depends on your cross-sectional area. If you tuck, you have less air resistance. That's why skydivers, you typically see them making themselves as big as possible because they'd like their terminal velocity to be as small as possible, even before they pull the parachute out. It's why it hurts so much more to belly flop into a pool than if you tuck and hit the pool smoothly. Looking at the parachutist above, what would the force of air resistance be once terminal velocity was reached? Well, we would take our air resistance equation. We had F air equals mg plus ma. Once you reach terminal velocity, what's your acceleration? And I guess the answer would just be mg. We can crunch it. What was it, 90? Times 9.8. Was the mass 90? Yeah. Is that what I said? I can do that in my head. That's going to be the same as 900 take away 18. 882? Double check me. Is it going to be 900 take away 18? Or is it 900 take away 8? No, 900 take away 18. 882, yes? Yeah? I multiplied by 10 because 9.8 is close to 10. And then I said it's going to be 0.2 times 90 less than 900. 2 times 9 is 18. 0.2 times 90 is 18. So in my head, I went 900 minus 18. I cheated. I multiplied by 10 and then tweaked the error. Tricks of the trade. Okay? A parachutist jumps out of an airplane, eventually I jump up, and free falls. They reach terminal speed and they maintain that speed for a while. Then they open their parachute, reaching a different terminal speed. Sketch of velocity. Do me a favor. Cross the word velocity out. Replace it with the word speed, because technically your velocity would be negative, which means, Robbie, I'd be drawing this below the x-axis the whole time, and I don't want to do that. So we'll just graph speed. Here's our sketch. Speed versus time. This is a sketch, not a formal physics graph. We're not going to worry about labeling the axes, putting a title, putting a scale, all that. We just want the shape. So, and really this is going to be vertical speed. So sitting in the airplane, what was my vertical speed before I jumped? So there should be some amount of time where the speed is 0. That's sitting in the plane. Is that okay, Ty? Then I jump. Ty, what happens to my vertical speed? Speed, not, first of all, not acceleration, speed, and it ditched the negative because we want to just bigger, smaller, or stays the same? Yeah. Now, eventually I'm going to hit terminal velocity, so don't write this down yet. Don't write this down. I don't think it'd be a straight line. Don't write that down. What would it look like? I think as I get faster, air resistance gets bigger, and so acceleration gets smaller. I think I accelerate at my maximum initially, but as I speed up, I kind of level off slowly. Remember, the slope of a speed versus time graph is acceleration. And so here, I'm accelerating less fast. Here, I'm accelerating faster. Here, I'm accelerating at 0. I'm at a constant speed. Is that okay? Then I pull my parachute. What happens? What happens to my speed? Let's say speed again, because otherwise, anytime you say velocity, I'm saying I'm still going down. I should be drawing it down here somewhere. I just don't want to do that. So speed decreases, increases, or stays the same, Max? Smoothly? When do I have maximum air resistance? Right when I pull my chute. Yes? When do I have minimum air resistance? right before terminal velocity. So I think it would look like this. I would slow down the fastest and kind of level off. And here is me in the parachute for a while. Now, my time scale is kind of garbage because this should be when I jumped out of an airplane. When I jumped out of an airplane, I drifted down for what seemed to be about 5 minutes, and I know I was only in free fall for about 30 seconds. So, okay. We're not going to worry about the scale. We're just going to get the shape right. What happens to my speed when I hit the ground? More specific, I can tell you exactly what my vertical speed ends up being. Yeah, I think something like that. I'm not quite sure what this section would look like. I've thought about it. It was just more of a bump. There's also a little section right here where my instructor backfills the chute to kind of bring us to almost a stop right before we hit the ground. I'm not quite sure what that would look like. But from the side, I think the parachute speed graph, it looks sort of like an old VW Beetle from the side. Yes? Do you guys want to watch the video of me jumping out of an airplane again? Okay.
I have to.
Okay.